Hi, welcome back to Power Electronics Lectures. In this video, I will talk about the diode and the RLC circuits. We'll see when we connect the diode to RLC circuit, how the behavior of the current and voltage will be inside the circuit. And we'll see also why it's not okay to switch an inductor directly within the circuit. Let's have a look at this circuit, which is a switched diode with RC load. Let's say we have a diode here, and this diode is switched by connecting a switch in series with this diode. All these connecting to a voltage source. And this combination is connected to an RC load. What we need to do is to switch on and off this switch at time, let's say this time equal to 0. Let's say we have here current I, and here we have voltage VR, and this is VC. And here, of course, the source voltage VS. The voltage VS is equal to VR plus VC, and VR is equal to how much? The current I times R plus the voltage on the capacitor is equal to how much? By definition, it's 1 over C integral from T0 to T for the current that is flowing in the capacitor, plus of course the initial condition. And this initial condition, let's say it's VC at time equals T0. If we try to convert this equation to Laplace transform, so you'll find that Vs small here, it will become Vs capital, and this will be equal to I of S times R plus the integral in time domain, it will be 1 over S in frequency domain, in S domain. So this will be I of S over S times C. Do some simplification for this circuit. You'll find that if you take I of S all together here, so this will be R plus 1 over SC, and this will be equal to Vs. Find the value of I of S. You'll find that I of S is equal to how much? Vs over R times S plus 1 over RC. And this is the current in S domain. If you try to convert this one to time domain using the Laplace transform table, so this will be in time domain how much? I of t. So if you remember, we said that if we have A over S plus B, so this definitely it's E to power minus B t times A, right? So here we have the same form. So I of t is equal to how much? V S over R times E to power minus 1 over RC times T. Okay? And this is the final expression of the current. Now we said in RC circuits or RLC circuits, what is the if you want to calculate the current, we care about the current inside the circuit and also the voltage across the capacitor. So now we found the current. Let's go and find the voltage across the capacitor. Now let's go and find the voltage across the capacitor. So we know that the equation of the voltage Vc of t is equal to how much? We just said 1 over C integral from the initial value, which is 0. We said t naught is equal to 0 to t, which is the time. So here for the current I of t dt. Okay, let's suppose that this initial value is for the current is 0, because let's say that the switch is open for a long period of time, so we make sure that there is no current inside the circuit. So suddenly we switch the switch, and then the current start develop inside the circuit. So this equals to how much? 1 over C. Now from the previous equation, we already found the value of the current, so we can replace it here. We can put it here, right? Instead of I of t, we can put Vs over R times e to power minus 1 over RC times t, right? Of course, dt. Okay. Now Vs over R, this one is a constant value. So we can take this Vs over R outside the integration. So this will be 1 Vs over Rc, integral from 0 to t for e to power 1 minus Rc times t dt. Okay. Now integration for e to power minus something is equal to how much? Is equal to e to power minus this something over the derivative of this value, which is minus 1 over RC. And this, of course, all together from 0 to t. Mathematics. Yeah? So this times, of course, the constant, which is Vs over RC. Right? So here substitute by t and by 0 and find the difference. You'll find that the final value for this capacitor voltage is equal to how much? Vs times 1 minus e power 1 minus Rc times t. Okay. Finally, we can write this value here. Vc of t is equal to Vs times 1 minus e to power minus 1 over Rc times t. And by this, we got the value for the expression of the capacitor voltage. We got the two values, the current and the voltage. Now let's try to calculate the rate of change of the capacitor voltage just by take the first derivative for Vc of t. So here you will find that the rate of change of the capacitor voltage is equal to how much? The first derivative, so Vs over Rc times e to power minus 1 over Rc times t. Now let's try to draw the current and the voltage to see how this current and voltage behave inside the circuit. If we connect RC load, we are interested in power electronics to see the behavior of the voltage and the current. So here, let's draw the current I of t and the voltage. Vc of t with respect to time. Now we know that the current is equal to how much? I of t is equal to Vs over R times exponential minus something, right? So this can be written like this, can be drawn like this. So here we have a maximum value here, which is Vs over R, and exponential function will go to 0. Okay? Now at this moment, when the time is equal to RC, so this value will be equal to how much? 0.368 Vs over R. This at time equals to RC at tau, the time constant. Okay? Let's go to the voltage, capacitor voltage. Capacitor voltage equals to how much? Vs times 1 minus e to power minus something. So it's exponential, but we will reverse this exponential and make 1 minus this value. So we'll get something like this. So we have this 1 times Vs is Vs. Okay, so the exponential will be this. Okay, now if you look at this moment when tau is equal to RC, okay, this value will be 0.632 of the Vs. So here, this is the 0.368 is e to power minus 1, and the 0.632 is what? 1 minus e to power minus 1. So in general, what we want to conclude by drawing these two curves, the current and the voltage behave this way. The current will reach to 0 slowly, and the voltage will come to the maximum value Vs also slowly. They cannot go directly to their maximum value or to 0, and this is very important in power electronics circuit. Having found the current and voltage in a switched RC circuit with a diode, now let's have a look at the switch diode with RL load. We are interested in inductive load. Okay, so let's say that we have this circuit, a diode with resistive plus inductive load, and this is connected to a switch And all this is supplied by a voltage source Vs. R, L, plus minus VR, plus minus VL, and here we have the current I. Okay, this switch closed at time equals to 0. Now, when the switch S conducts at t equals to 0, the current I in the inductor increases. Okay, so here what's happening? Vs is equal to VR plus VL. This voltage here, Vs, is equal to how much? The voltage from here to here plus the voltage from here to here, right? Because this now it's short circuit when this switch is conducting, and the diode will be in the forward bias, so both should be considered as a short circuit. So this will be equal to how much? VR plus L di by dt, right? And you know that VR is how much? I times R, so this will be I times R plus L di by dt. Now when all initial conditions are zeros, so we can easily convert this equation to Laplace transform. So this will be Vs over S equals to R times I capital of S plus the derivatives in time domain is equal to how much? S in S domain. So this will be L times S I of S. Okay. Also go and make some simplification here. You'll find that I of S equals to Vs over S times R plus Ls. And this will be equal to how much? Vs over L, just divide by L, both upper and lower side. So this S times S plus R over L. Okay. Now you can use partial fraction to divide these into two parts. So this I of S is equal to how much? Vs over R times 1 over S minus 1 over S plus R over L. Now this from Laplace transform table you can convert it easily. So you can say I of t equals to Vs over R times 1 over S is what? Is 1 step, right? Step function minus again 1 over S plus something is e to power minus something. So e to power minus R over L times t. Okay. And this is the current that is flowing in a diode circuit with RL load. Now, the rate of change of the current, rate of change of the current I, which is di by dt, we can find this by take the first derivative of the current expression, right? So is equal to how much? Di by dt Vs over L e to power minus R over L times t. Okay, now we can use this expression to find the voltage across the inductor. We know that any voltage across any inductor is equal to how much? VL? L di by dt. So we can replace this one, substitute by this equation. So we can say this VL of t is equal to how much? Vs times e to power minus r over L times t. Okay, and this is the expression of the voltage across the inductor. If we try to draw the relationship between time and voltage, we can easily draw this equation here. The maximum is Vs at 0, because when this is 0, so e to power 0, how much? 1, right? 1 times Vs, Vs, right? So this is VL of t. And this exponential function will start falling to 0 exponentially. And the current value? I of t. Now notice that the current inside the resistor when t equals to 0, how much? 0, right? There's no current. And then the voltage, if there's no current at time equals 0, then the voltage will be 0, right? So when the voltage is 0, so I of t here will start, of course, at 0. Or you can easily substitute by the value. So this will be how much? So here's Vs over R. This value is Vs over R, right? And here, at time constant, now the time constant is equal to how much? L over R. Okay? So at tau is L over R, and here also L over R. How much the value of the current and voltage? So this will be 0.368 Vs, and this will be 0.632 Is, right? Again, this value is 1 minus e to power minus 1, and this value is how much? 0.368, which is e to power minus 1. Now, what we care much here about is what? The behavior of the current and the voltage inside the RL load. Now, if you remember, for the RC circuit, the current is falling down to 0 exponentially. But here, the current is rising exponentially. For the voltage on the RC circuit, the voltage is rising exponentially. For the RL load, the voltage is falling exponentially. Now, the problem is not in closing the switch in RL load. We can close the switch, no problem. There is no energy stored inside the inductor, no problems. So when we close the switch, everything seems beautiful. There is no problem because the current will start developing inside the circuit. The problem if we want to open the circuit, we have energy stored inside the inductor, okay, and we have a switch. We want to open this switch and make the circuit. We just open circuit. What's happening at that moment? We already have energy stored inside the inductor. This energy needs a way, or needs a path inside the circuit to go through this path to be dissipated inside, let's say, a resistor. Okay? But if we don't have this path, we have a big problem, and this big problem can cause spike or energy losses, and also this spark can damage the switch, because the only thing that we can deal with in this circuit is what? The switch. If we open the switch, all the energy stored inside the inductor will go to this switch and be dissipated in that switch and will damage the switch. So that's why in diode RL circuits, we need another path, or we need something we call the freewheeling diode. This freewheeling diode will make another path, additional path, for the current to be flowing if the diode happens to be open. Okay? Now let's study the behavior of the current when we switch on the transistor or the switch, and see how dangerous this energy stored inside the inductor, and why it's not okay to switch on or off the inductor without providing any additional path. To simplify the problem or the concept of the switched current, the switch inductor, let's draw this circuit. Let's say that we have the voltage source here. This voltage source is 10 volt, and this 10 volt is connected to a resistor, and this resistor is 1 ohm. Okay, and all this circuit is connected to another inductor here. Let's say that we have 100 inductor here, a bit large inductor, and also here we have another resistor, and this resistor is 1 kilo ohms. And here we have a switch, and this switch is connected like this to the position, let's say A, and this is position B, and we need to switch this from A to B. Okay, now when the switch is at position A, at time equals to 0, the current is equal to how much? At that moment, we will expect that the current is equal to 0 at time equals to 0. Okay, just imagine that there is no current at the beginning, so the initial condition should be 0. Okay, the voltage, because there is no current, the voltage on the resistor VR here is equal to how much? Also will be equal to 0, and the voltage VL at that moment, the voltage here VL is equal to how much? Is equal to 10 volt. Why? Because before connecting this switch here, we have open circuit, right? Open circuit, no current on this resistor, no voltage on this resistor. So at time 0 exactly, when we connect this, there's no current, and the voltage here that applied on this inductor will be exactly equals to how much? The voltage coming from the source. Okay, if we try to draw this current developing in this circuit, so here we have I of t, The current will be 0 at the beginning. It will be developed until it reaches how much? 10 amperes. Right? Let's see how this 10 amperes come from, where this 10 comes from. Now at time t equals to t1, let's say at this moment, this is t1, okay? VR is equal to how much? The voltage across the resistor is equal to 10 volt, because after certain period of time, this will be wire, okay? And the total voltage on the resistor will be equal exactly to the voltage across the voltage source. The voltage VL is equal to how much? 0, okay? And the current I is equal to how much? We have 1 ohm resistor, and this 1 ohm resistor has a voltage of 10 volt, so the current will be 10 amperes. Okay, so at this moment will be 10 amperes. Now, at time t equals to t1, let's say we switch to position B, to 1 kilo ohm resistor. Let's repeat our calculation. Now IL at that moment is equal to how much? 10 amperes. We know that. And the current in the 1 kilo ohms resistance is equal to how much? 10 amperes. Right? And the voltage across that resistor, the 1 kilo ohm resistor, and we have current 10 amperes, and we have 1 kilo ohms, so the voltage is I times R, so 10 amperes times 1 kilo ohms, how much? 10,000 volt. Imagine that. So the voltage across this resistor is 10,000 volt, and because now we connected this switch here, so the voltage on this inductor will be how much? Also it will be 10,000 volt. So VL is also equal to how much? 10,000 volt. Now we know that VL is equal to how much? LdI by dt. Okay, let's calculate the rate of change of this current. So di by dt is equal to how much? VL over how much? L, which is 1 Henry. VL is equal to how much? 10 kilovolts. And L is 1 Henry. So di by dt is equal to how much? 10,000. So the rate of change of the current is 10,000 amperes per second. So we expect that the change of the current here at this moment will be how much? The slope will be 10,000 ampere per second. The slope here, now look, the slope here is 10,000 amperes per second. The slope here is how much? 0. Because we have steady state current. Okay, now the rate of change of the current, imagine 10,000 amperes per second. Where this 10,000 ampere will go? So this means spike. Spark is huge current, huge charge needs to be dissipated somewhere. If we don't provide path for this current, then we will damage our circuit. So that's why it's not okay, it's dangerous to switch off the inductor directly. We need to provide path. This path should provide a way for the current to be dissipated somewhere, either in a resistor or to supply a load or to do anything else inside the circuit. Okay, I'll stop here for this video, and next time we'll talk about a new concept, which is the freewheeling diode. So see you next time.